Then okay, I hope you can see my screen.
Yes, sir.
Good. Okay, then I will switch to this chat window. Okay, so today's topic is profiling your programs. Okay, in particular, we will talk about how to use the GNU profiler called gprof. Okay, so why profiling? Okay, so what you have so far done, you have learned quite a bit about the C programming language and the C compiler in particular. And you know how to write make files to build big projects. Okay. And in the last 2 weeks, you have seen how you can use a debugger to remove implementation and logical bugs. And that includes the GNU debugger GDB. And for memory related problems, leakage, overflow, that kind of stuff, you use some tool called Valgrind. Okay, but we have, or you have not yet looked at how efficient your program is. Okay, so how efficient your program is in terms of, I would say, running time, which is of the primary concern in this talk. Space usage is another thing, but anyway, I will not talk about that. Okay. So, okay, I have now a program which is free of implementation bugs, logical bugs, okay, but maybe its performance is poor, okay. So I have to identify what are the sources of inefficiency in my code, okay, and a profiler like gprof helps us to achieve that, okay. In fact, to be very precise, what gprof does, it makes a, yeah. Was there a question or just random interference? Okay, I think so.
Sir, it was an echo.
Okay, fine, something like that. Okay. Now, gprof is a tool, an abbreviation of GNU profiler, which helps you in understanding the relative performance, and also I would not say not only relative, but absolute performance of the functions in your program. Okay. And the performance of a function in a program may be poor in 2 ways. Okay. One, each invocation of the function takes too much time. And the second possibility is that that function is called too many times. Okay. So these are two potential sources of inefficiency of a function. And we need to identify some automated tool that helps us understand how our different functions work. Okay. In absolute terms and also with respect to relative performance. Okay. And gprof actually helps you to detect both. Okay. In particular, the first issue is invocation of the function takes too much time. So how much time in absolute terms or in relative terms your functions are taking? And the so-called flat profile of GNU profiler gives you this detailed data corresponding to this first point. And the call graph generated by gprof tells which functions call which functions and how many times. Okay, so both the issues are addressed by the profiler. And once you know that this is the relative performance, so you essentially look at the functions which are relatively performing pretty poorly. You should look at the function code and think about improving the performance. Okay. And that improvement may mean better implementation, better use of data structures, or even design of better algorithms. Okay. And call graph will tell you how many times each function is called. And if that is too much, and if it is avoidable, gprof will tell you this is taking too much time, so you do something about it. But doing something about it is not gprof's business. You have to look at the functions and try to minimize the number of calls. So I will illustrate both these aspects of gprof by using several examples. Okay. But before going to those examples, let me first tell you how to use gprof as a tool from the command line. Okay, how to run it. Okay, so first of all, when you compile, okay, you should give this extra option -pg. Okay, then your a.out or whatever you specify as -o, that executable file, will contain some extra information that will help you, not you exactly, I would say, that will help gprof to do some kind of profiling of your executable file when it is running. Okay. So this is the important thing. Compile with the -pg option. Okay, so this is the first thing you need to do. Then you run it by simply calling a.out with some parameters or not, whatever. This actually creates a profile data file with the default name of gmon.out. Okay. I think at some stage you may actually supply a name of this gprof output file, but let us not worry too much about this. I think it may be here. It should be here, of course, not here, because that's your code running. So maybe you specify the name of this gprof output file by supplying some option here. Okay, but anyway, let's not worry too much about it. The default file, the data file generated by profiler is this. Okay, as of now, you do not see any profiling information. But once you compile and run, then this file is created. And this stores all the information about the relative performance, or I would say about the flat profile and the call graph. Okay. Everything is stored here for this run. Okay. If you run your a.out or executable file once more, this will be overwritten. Okay. Now what you have to do, in the third stage, you call gprof. Once again, give it a name, a.out, because it needs the symbols, function names and other stuff. That is why you are giving a.out to gprof. And also you say that this is the output file generated by the profiler. If this is omitted, gprof will search for this file. So unless you I would say, have generated a different file, you do not need to supply any name here. Okay, because this is the default file that the profiler will search. Then looking at the symbols of a.out and whatever is written here or any other file, profiler will give you some detailed information. Okay. Note that when you call, unlike Valgrind or GDB, when you call gprof, it is not running a.out. It has to be done previously and independently, provided that your program is compiled with -pg option. This file will be generated. If it is not compiled with this option, then of course no file of this form will be generated, and you cannot use gprof. Okay. So gprof a.out does not run a.out. It still requires this in order to know the symbols, function names, and all other stuff. And it only reads this and looking at the symbols here, it will give you some detailed profiling data. Okay. And that data includes this, the flat profile, which you also can call timing profile, the call graph, also some detailed instruction on how to interpret the above two tables. Okay, so it will generate a table here, generate another table here, and it will also give a detailed instruction. In any case, I will also tell about these instructions, even though every run of gprof will give you this instruction. Okay.
Sir?
Yeah, tell.
Sir, this gmon.out is made during the run, means the run time of the a.out, or it is formed when the a.out is formed?
No, not. It's generated by this, the run.
Running of a.out.
Yeah, provided that you have given the option -pg.
Okay, okay, sir.
Okay, if you do not give this option, no such file will be created. You run it 100 times, a million times, it doesn't matter. Okay, and every time you run a.out, your old.gmon.out will be overwritten. Okay, and once again, let me mention gprof does not run a.out. It requires this file to know the symbols and all other stuff. It reads only this and gives you this profiling information. This is the difference between Valgrind GDB with Valgrind.gdb and this. Okay, it does not run a.out. Okay.
Yes, sir.
Okay. Okay. So before looking at this flat profile and call graph, let me give you just some, I would say, additional options. If you want to, for example, do not want these detailed instructions. Okay, you run it once, twice, you will see the same instructions are coming. Once you know this, possibly you are not very much interested in saying these instructions because you know this is a standard constant set of instructions. Okay. So if you do not want, of course, your important things are the profiling, timing profile and the call graph. Okay. So these things are pertaining to your code. This instruction, if you want to suppress, just call it with -b option. And if you are interested only in the flat profile, you run it with -p. And if you do not want that, run it with -P. And if you want to obtain the flat profile for only a single function, write it as p, that function name. And I believe you are not permitted to write a space here. Yeah, you are not permitted to write a space here. So -p followed by my function, whatever name it is. Okay. And likewise, we have the two options for the call graph. -q, print only the call graph. -Q, do not print the call graph. So it looks like -q and -p are essentially, -P and -q are essentially the same. And anyway, you have these options. This is another important and interesting thing. Print the information of all functions. Okay. We will soon see examples where GNU Profiler suppresses information about certain functions which take practically no time, okay, or which are not even called. Okay, but if you say -z, you will see all functions, and you will see some funny-looking functions. We will come to that later. Now, this is something. This was a function level profiling, as I mentioned. Okay. If you want to make a line-by-line profiling, you should compile with -g and -pg, both options. But the problem is that with the recent versions of GCC, gprof cannot reliably or meaningfully give you a line-by-line profiling. It tries to do something, but with the new GCC compilers, this line-by-line profiling, I would say, makes very little sense. If you want to make a line-by-line profiling, so this line is executed this time, this many times, this line is executed this many times, and so on, instead of so not only so many times, and took a total of this much time. Okay, if you want that kind of line-by-line profiling with modern GCC compilers, you use GCOV. This is another profiler prepared for line-by-line profiling, but anyway, we will not cover GCOV. Okay. So let us stay happy with a function level profiling only, which gprof can do. Okay, so now let us
line by line profiling, like time for each line to execute.
Time for each line, how many times that line is executed, that kind of stuff. Instead of in the level of functions, it is in the level of lines. Okay, so that's a more, I would say, finer profiler. Okay, the resolution is line, not functions. Okay, if you are interested, you can learn how GCOV works. It's fairly straightforward. Okay, but anyway, we will not cover GCOV. Okay, so now let us look at these two types of profiling information. One is timing and second one is call graph. Okay. So it's basically a table, okay, which consists of the following: a listing of the functions in your program with profiling information, okay, and you have a summary. Each line tells something about that function, and so this includes the following topics: percentage of time, okay, the percentage of time spent by the program while it was in that function, but you have to exclude the time spent in other function calls, if any, of course, made from this function. Only when that execution was in that function, forget about the time spent in the called functions and caller functions. Okay, so that is called the percentage of time.
Sir,
okay. Yeah.
Sir, in this thing, what if there is a function and inside that function there are some other functions?
Yeah.
So what happens in that case?
We will see. We will see. Function f calls function g, let's say. Okay. So, but this execution was in function f for some point of time. When it goes to g, this is no longer counted here. Okay. So we will see. We'll see examples.
Okay, sir.
Okay, so that means that if you have some n number of functions and if you add those percentage times for the functions, it should add up to 100. Okay, because at every point of time you are in one of the functions starting from main. Okay, but we will see that this rarely happens because GNU profiler is not a, I would say, exact estimator. But anyway, why it is so, we will see later. Okay. Now this is time. Okay. Spent inside the function. This is no longer percentage, but it is absolute time. Seconds, millisecond, nanosecond, microsecond, something like that. And this cumulative time and this listing is sorted with respect to the decreasing order of these self times. Okay. And there is something called a cumulative time. I do not really understand the significance of this time. It is the sum of all the self times, okay, of this function plus the self times of functions appearing above this function in the table. So there is nothing called called, caller, and all that kind of stuff. But the table has something, and If you are at row n, talking about the nth function, then this cumulative time is the self time of function 1 plus self time of function 2 plus self time of function 3, blah, 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 up to self time of function n. Okay. That's the interpretation. This has nothing to do with calling caller or called functions. Okay. It's just a sum of the self times of the functions appearing above this function in the table. Plus, of course, the time spent by this function. Okay. Then number of times this function is called and average self time per call. Okay. The number of times this function is called and the average. So it is basically self time by number of calls. Okay. In fact, we will see more detailed information about the number of calls, who called whom, and so on in the call graph. So let us not worry too much about these calls when we are talking about the flat profile or the timing profile. Okay. And the average self time per call. And this is reported in seconds. S. It uses this abbreviation ms, milliseconds, US. Just think of some one line here, so it looks like microsecond. Okay. Nanosecond, if it is even smaller, maybe what is the next smaller thing? Pico, right? Maybe PS.
Yes, sir.
Femto may be even smaller, FS. Okay. Usually it's in this range, second, millisecond, microsecond, or nanosecond. Okay.
Sir, in cumulative time, if a function is called multiple times, will it be listed again and again?
No. This is the total summary. This is a summary.
Okay, sir.
Okay, not individual calls. Total time per call. I mean, total time for each function. And this is average time per call for each function. Okay. And what else? Average total time per call. Now this includes called functions. Okay, self time plus the time spent in other function calls made from this function. Okay. This somewhat makes sense, but this has nothing to do with this cumulative time. Okay. Once again, it is usually reported in second, millisecond, microsecond, or nanosecond. Okay, so let us see an example. Oh, I see. Okay. So the idea is that this is absolute performance of one call, excluding the, I would say, nested function calls you make. This is the time for each function, including the nested calls, if any, made from this function. These are the absolute times, of course, averaged over all the number of invocations of that function. And this is percentage of time. So this is the relative performance. This is the total absolute performance. This is the average absolute performance. Okay. So this, and this, topic 2, 5, and 6 are absolute performance. And this percentage of time, this is the relative performance. Okay. The trouble is that GNU Profiler gives you only an approximate estimate. Okay. And these estimates must not be considered as fully accurate. Okay. This is just giving you an indication of these things, percentage of time and all this stuff. Okay. So it's only an approximate estimate of this performance. Okay. And why approximate? it does not keep on monitoring your program continuously. Okay. Instead, what it does, every 10 milliseconds, it makes a sample of the execution of the program. It takes a snapshot. Okay. And based upon that samples, those samples, it makes this estimate, a statistical estimate. Okay. But since this is not a continuous estimation, continuous monitoring, okay, it has to be a rough statistical estimate. Okay. But more often than not, this approximate or rough statistical analysis is good enough for you to have an educated understanding of your function's performance. Okay. But since this sampling time is something like 10 milliseconds, and if your code runs for, let's say, 5 milliseconds, then it's possible that gprof never gets any chance to sample your code. Now, even if it is run for something like 20 milliseconds, so at most 2 samples are provided or generated or obtained by gprof, the sampler. Okay. So with 2 samples, a statistical analysis will be a bit too bad, right? So you need to understand this. You need to give gprof some time for gathering sufficiently many samples to make some meaningful estimates. In other words, you need something like at least 100 samples, 1,000 samples. Let's say 1,000 samples is a good thing. Okay. And if it is 1,000 samples and if its sampling time is something like 10 milliseconds, how long will your program run? This is 1/100. And if you want to have something like 1,000 samples, so 10 seconds. Okay. So your program should run for at least a few seconds. I would say 10 seconds or little more. At least 5 to 10 seconds is the minimum. If your program runs for less than this much time, then the profiler is not expected to give you a reasonable or meaningful estimate. Okay. And
Sir?
yeah, tell.
Sir, if you're saying that it should be at least more than 0.01 second, sir, so how are we sure about that kind of data it would be able to provide us? The
Yeah, that's what I told.
accuracy of that is extending up to nanoseconds. So, sir, how is that
That is
possible?
by distribution by number of calls and all that stuff. That's why I mentioned, look at this. This average time is nanosecond, millisecond. This is something, but this is when you divide by the number of calls. Okay.
Okay.
This time, self time, what I was talking about, this should be of the order of seconds. And then you divide by 1 million, 1 billion, you may end up in some microsecond, nanosecond, millisecond type of times. Okay, this is again an estimate. This is an estimate. And this is that estimate divided by the number of calls. Okay. So that's not a problem, right? But the frustrating thing is that, so maybe you ask gprofiler instead of sampling every 10 milliseconds, you sample every 10 microseconds so that the accuracy will be even larger. Unfortunately, this cannot be done. Okay. You cannot change the default sampling rate by any option. It is predefined during compile time. Okay. So you cannot change this. Okay.
Sir, one more thing.
Yeah, tell.
Sir, whenever we run any program, so the total time taken to execute it often depends on the state of the machine it is in currently. So every time we run the program, it might give us different result. I mean, different performance.
Yeah, that's true. That's true. That's true. Variations will always happen. Okay, it depends upon at what point of time it is sampling your program and all that stuff. But it is sampling execution of your program.
Can I say something?
Yeah, tell.
Yeah. So you have to understand why you want to use gprof. Okay. See, first of all, if your program anyway takes 100 milliseconds, 1 second, you don't need gprof. Gprof is used basically for large programs, okay, to identify performance bottlenecks. So first of all, that it is a 0.01 is not a big deal basically. That's not exactly accurate, it's not a big deal basically. Because the exact value of how much time it took is really unimportant to you. Okay. So it's okay, it would have been better, but most programs that you want to use gprof with so that you can speed them up will run in order of seconds anyway. Otherwise, gprof, trying to speed them up is not very useful anyway. Okay. The second thing is, yes, if you run it on different machines, it will vary. The actual time, the absolute time will vary. But if you look at the data, first of all, the percentage of time thing shows you is a relative thing. If you have 10 functions, it will still show you that if your function, total program is taking some 100 units of time, which is the function which is being called more number of times, taking the most amount of time, most average number of time, and so on. So the idea is to run gprof to figure out which part of your program do you want to concentrate on to improve its performance. So fine, in one case, if you run it on a very slow machine, it may take 200 seconds. If you run it on a very fast server, it may take 50 seconds. That much difference doesn't happen, but suppose. But if you look at the proportion, and if you feel that 50 seconds is also high, and you look at the proportion, then it will give you an idea about which functions you should focus on improving, where are most of the calls going. So that's the data you want. The absolute exact times are not very important. Okay, I'm done.
Yeah. Okay. Okay, so again, this point says that since these are only rough estimates, the percentage estimate should add up to exactly 100, but it is usually not the case. Maybe less than or even larger than 100. Okay. But again, as AG mentioned, you don't need to worry about this. It's sufficient that you consistently see that your function F1 is taking too much time, too much percentage of time, that kind of stuff. Okay. Whether or not they add up to 100, it usually doesn't matter. Okay, maybe close to 100.
Sir.
Yeah.
Sir, suppose we are doing some sort of input, taking input from the user, then like how is that time considered as run in the runtime, or what is done exactly over there?
Okay, I think that will add.
If you have a scanf inside a function, okay, it's still inside that function. That's the time the function is taking.
Okay. Yes,
so it will still add basically.
No,
but we have to check that because there is this notion of, you will learn in third year, it's a notion of CPU time and IO time. So when you wait for a scanf, your process actually does not use the CPU.
Yes, yeah.
Okay. So what you want to see, if somebody enters an integer 10 minutes late, you cannot call your program slow, basically. It's a good question, which we will confirm and let you know whether it's the CPU time only or it's the. It will be easy to write a program and check that.
Yeah.
We'll do that.
But my understanding is that this should be CPU time.
Yeah, it should be CPU time because that's what we want to optimize. So IO time probably will not be counted.
Yeah, IO time does not, does not keep the CPU busy anyway. Yeah, it should not count.
Excuse me, sir.
Yeah.
Sir, like, is there a reason why is it 0.01 second? Like, why is it not less than that? Like, why the developers didn't make it lesser?
This is a very difficult question. I am not a developer, but in my experience says that there are other calls also which measures time in this resolution. I mean 10 millisecond resolution. So that may be a particular choice of the C development teams. Yeah, but AG, are you
So we have to check on that basically. So why they made it 0.01 is tough to say exactly why 0.01. But there are several issues. One you have already mentioned. Okay, there are time resolutions of other things. The other thing, I'll try to find out and let you know later. The other thing that you should be very careful when you do any sort of time measurement is that note that when it takes the sample, okay, it's the same program running basically. When it takes the sample and does something, okay, actually it's running on the gmon.out, right? Yeah, so that no, that should not matter because it's not a online monitoring basically. It's got the offline file. Okay. So it don't affect the time. So frankly, I don't know. Basically, it came from maybe from some, as you said, timing resolution that used to occur at that time and so on.
Yes, sir. Okay, sir. So because I was asking,
I'll try to find out.
Yeah, sir. I was asking because like our CPU is in like nanosecond range, the clock time of CPU. So like we can.
Yeah, but you have to understand the two things out there. Okay, one is many of these tools are old. Okay, so and the other thing is that your desktop CPU is in that range, but as somebody has mentioned about something, some CPUs may be very old also, but they have to build one tool or something. So ideal case would have been, as Eddie has said, that have a default thing, but give the user an option of changing the sample time basically. Which some of the other profiling tools I think does basically, but gprof does not. Basically, doesn't give you that option. I'll try to see if there's a history behind this. Okay.
Yeah.
But
okay.
Not sure right now.
Okay. Sir, one more doubt.
Yeah, tell.
Sir, suppose we are using some math library in the function, then that function call is treated as separate?
Of course.
Okay. Then scanf and printf should also be treated as separate things.
Yes.
Because
True.
Okay.
True. That is true. They are also function calls. But when the program is waiting, the executable file, the execution is waiting for the user to enter something, the CPU is not doing anything.
Yes, sir. Understood.
Okay.
Yes.
Okay. So that timing should not count. This is my understanding.
Okay, sir. I will try out this.
Okay. So it is waiting for you. And that is, you are not part of the CPU. Okay. Yeah. So that's it.
So suppose we are running a program and it takes say 5 seconds. Now if we run like gprof, so it is taking samples at every 0.01 second. So like, will it like slow down the running of the program a little bit?
That it may do.
No, it don't. See, this is what I was started and then I stopped. So let me digress a bit, if you allow me, Praviti. Right. So whenever you measure, so when there is something like online measurement, online means what you just described. While something is running, you inject some measuring method into it basically. So there you have to be very careful about the time. So that because you're trying to measure the performance of a program, but the measurement tool that you introduce, which also takes some time, should not change that time considerably. Okay? So had this been an online measurement, kind of online profiling, that while the program is running, it is profiling things, then it wouldn't matter. Okay? So
no. I mean generation of that gmon.out.
Right. So that is just basically timing information that is generated.
Yeah. So that would take some time.
So that will slow down slightly, but this 0.01 millisecond sample, okay, yeah, generation will slow it down a little bit, but then the gprof analysis will probably not slow it much, basically.
Yeah, but
yes, the timing thing introduction, yes, you are right. The timing thing introduction will slow down somewhat. Maybe now then going back to the old question, okay, so then what we were started thinking is probably right, basically, because if you so if you introduce this, so think of the program running, okay, when you compile with -p. So basically it will put certain things in the program, okay, so that when gprof reads that gmon.out file later on, okay, it will get some information every 0.01 seconds, basically. Okay. So first of all, getting that information and writing it to the file takes time. So if you do it too often, okay, then the total time of the program gets affected by it, basically. Okay. So there is an issue out there. So there is some online thing going on and you don't want to do it too often, otherwise it will slow down your program too much basically. But let us look into it a little bit more detail and get back to you.
Yeah, so that may be a reason why 10 millisecond is a good quantum of measurement. Yeah.
Okay. So let's try to find out basically just for curiosity's sake later on that what exactly gprof puts in that Gmon file basically.
Yeah.
Okay, we'll do that. We'll do that and get back to you.
Sir.
Yeah.
Does gprof does error correction on the time measurement?
Error correction? It's just an estimator.
Like if like it was taking like some X seconds and the gprof has introduced like some Y time extra, so it is.
Oh, absolutely, absolutely. Okay, so if gprof does X plus Y, okay, and then you have a actual user program function, the function's time gets completely changed because gprof is taking time, then nobody will use gprof. Okay, so I would not use the word error correction. Okay, but
that sense you asked the question. Okay, now I think it's.
I would not say error correction, but it definitely you will get an estimate of the F1's actual time. May not be exactly accurate, but an estimate of it. So the relative performance of your different functions in your user program will kind of more or less stay the same. But as I said earlier, the exact value, whether it is 5 nanosecond here and there, does not really matter. Okay. But again, this has linked with, it would be good to find out. We'll find that out and tell you in the next class that exactly what is written in that Gmon file, basically. But the results that you get are still going to be quite correct, basically, in terms of relative performance of the functions and the actual times taken by the functions on that machine.
Okay, so yeah, so functions that are not called or that miss the samples are not listed. However, you can run with the -z option to list all functions. Okay. And this is another thing you should always, I would say, stay prepared to see some functions like this frame_dummy, which you didn't write. From where did this function appear? Okay. In fact, we'll see that in addition to whatever functions you have written, main, F1, F2, F3, and all those functions, you will see some such functions which you didn't write. Okay. But these functions are called by the runtime system and should account for a very small percentage of the total time. If they take too much time, okay, then there is something wrong in your code. Okay. Anyway, these functions are not in your control. They will always run. Okay. Okay, so, and this is already I mentioned, gprof, at least with the current version of GCC, is, I would say, designed to make a function level profiling. For line by line profiling, you should use another profiler called gconf. Okay. Okay, so I would say that this is already enough of theory. Let us look at the sample output. Okay. So let's see the profiler, I mean the options, -b. Okay, what does -b say? Do not issue those, instructions. Okay. -b says the print flat profile only. -z means all functions, including those that take 0% time. Okay. And we will soon see a function with these functions. So next number is happy main. And I think these are some of the functions that you wrote. The remaining functions, frame dummy, do global detours, aux, whatever. Okay, Gmon start, blah, blah, blah. All these functions are not written by you. Somehow, these things are still executed because during runtime, these functions appear. Okay. In any case, you see that this case, starting from this, they are taking essentially 0% time. So this is usually the behavior. Okay, these functions should add up to a very small percentage, very close to 0% of the total running time. Okay, so you can actually ignore these things. Okay, but be prepared to see some such unknown functions. Okay, so that's the reason I have run the profiler with the -z option. List all functions. Okay, for us, these three functions are most important. Next number is happy and main. Okay. Anyway, in the next few slides, what I will demonstrate is how this flat profile, this times percentage relative performance, and the total times per call, they give you an indication on which function I should work on in order to improve the overall performance of my code. Okay. So,
Sir,
yeah.
Sir, the time of frame dummy and the functions below it, it's not counted in cumulative seconds, right?
Why not?
So because it is not counted, like 0.58.
58. No, 58 plus 9, that is 67.
67 and 370.
370, okay. So again, this may be some approximation, floating point approximation. So it has become 70.
Okay, sir.
Maybe 705, something like that. Okay.
Okay, sir, got it. Thank you, sir.
Okay. Okay. So I am mostly interested in my functions. These functions in general take an insignificant percent of time, maybe 1%, 0%, 1%, something like that. We may actually do not worry about those things. Okay. Okay, so I will give you a complete example. Okay. So let n be a positive integer. Let me first define a concept called happy numbers. Let n be a positive integer. So what I will do in a loop, I will replace n by the sum of squares of the decimal digits of n. Okay. And we will see if n eventually reduces to 1, then this initial n, and in fact all the intermediate values of n generated in the process is called or are called happy. Okay. And if it does not reduce to 1, what will happen? This sequence will eventually become periodic and keeps on looping without ever reaching 1. So all the numbers generated in such a sequence are called unhappy or sad. Okay, so here is an example. So let's see 2020. Replace 2020 to 2020 by 2022 by 2 square plus 0 square plus 2 square plus 2 square, which happens to be 12. Again, this replaced by 1 square plus 2 square, 5, 25. Then 2 square plus 5 square, 29, 85, 89, 145, 42. Okay. And you see that after these many iterations, 89 is repeated. This is the first repetition. Okay. What does it imply? It implies that the next one will be 145, then 42, then 24, 16, 37. So this will keep on repeating this loop. Okay, it will never reach 1. So 2022 is unhappy. In fact, turns out that 2026 is the first number after 2022, which is happy. And this is the reason 2026 is happy, because 2 square plus 0 square plus 2 square plus is 44. Then 44 becomes 4 square plus 4 square, 32, 3 square plus 2 square, 13, 1 square plus 3 square, 10. 1 square plus 0 square 1. After this, it will keep on looping in 1 itself. 1 square is 1, 1 square is 1. Okay. So now what I want to do is write an efficient function for checking whether the number is happy or not. Okay, so this is just a small toy example, but this will illustrate that something may go horribly wrong if you do not worry about performance analysis. Okay. And how do I check the performance? Maybe I will call this function for all n in the range 1 to, this is how much? 10 power 5, 100,000. Okay. In fact, I will adjust this range, or for that matter, I will embed this code inside another loop so that my program always takes something like 5 to 10 seconds. Okay. Okay, and then I'll just divide the total thing by the number of calls to get the per call performance of this function. Okay, so to start with, I will write, or I will design an algorithm and implement that, which is certainly very bad. And I will explain to you how I can iteratively improve the performance of the code by looking at the flat profile or timing profile, which will identify there is a problem with this function, do something about it. So I will do, make it a little bit faster. Then I will see, okay, this is better, but still not good enough. Eventually, I arrive at a, I would say, reasonably good implementation. Okay, so you see that first idea is that if I find if this thing eventually reduces to 1, then of course I know this is happy. Otherwise, I have to find the cyclic behavior. Okay. So here this 89 is the first thing that is repeated. Okay. What if 85 was repeated? 25 may have been repeated. Okay. So the idea is that whichever numbers are generated so far will be remembered. Okay. And whenever a new number is generated, we will see whether that is generated earlier. So here 89 is generated earlier, and this is the first time I am detecting this. Okay. So I am declaring it as unhappy. Or if I ever reduce 1, I immediately declare that number to be happy. So I have to detect a cycle. Okay. And for that matter, I have to remember what numbers are generated so far. Okay. So to start with, what I will do, I will have these functions. So is happy when input n, it returns 1 if n is happy, 0 if not. Okay. And I will also have a function called next number, which returns the sum of the squares of the digits of n in order to generate the next element in the sequence. Okay. And I will use a data structure which is initialized to record that no number is generated in the sequence so far. This is the initial thing. Then when some number is generated in the sequence, okay, I will also have a function to check whether n is already generated in the sequence. Okay. And when n is generated, mark in A that n is already generated in the sequence. Okay. And we have a main function which calls is happy n for n in the range 1 through 10 power 5 and prints n if and only if the call returns 1. Okay. So Here is a high-level description of this function is happy n, and I am interested in making this function as efficient as I can. So I initialize the data structure A. Okay. Then n is the first element in the sequence. So I mark in the data structure A that n is visited. And then I keep on looping, generate the next number. If it is not so far visited, I will mark it as visited and continue. Okay, generate the next number, do the same stuff. If it is visited already, okay, then I will check whether n is equal to 1. If so, I will return 1. Otherwise, it is in some other cycle, I will return 0. Okay, no problem, right? Okay, so this is a fairly straightforward thing. So somehow I have to make this A more concrete in order to have a working code for this program. Okay, so we start with a deliberately bad first attempt. Okay, so A is an array of size n plus 1. Okay, or 200 if n is less than 100. So there is a reason for this. We'll see later. Okay, so I will set all the cells of this array A equal to 0. Okay. So I stands for whether I is visited in the sequence already or not. Okay. So this is kind of a hash table without any collision possibility. Okay. I will always map to AI. Okay. So is visited n, just check whether n is equal to 1. Okay. And mark visited. Set n equal to 1. It's a fairly straightforward implementation. Okay, so I think you understand that this is a hash table without any collision probability. Okay, without any collision. Okay, so now if I run this code on this data structure, I see that this is the percentage time. For 99.15% of the time, the program was in the init call. Okay. And a little bit time is spent in the is visited thing. Mark visited essentially does not take any time. Next number also essentially does not take any time. And is happy, which is the final thing. Okay. This takes only very small amount of time. Okay. Most of the time is spent in that init thing. Okay. And total time per call for init is 93.20. This is 0.101. And this is the final goal. This is 93.3. This is microsecond. So remember this, it's something like 100 microsecond. Okay. So this array is good. Is visited is just a check for an array location. Mark visited is also very efficient. Okay. Set that array location to 1. But this init is very costly because you have to set all the cells AI equal to 0. So I have to do something about this init function. I have to make it better. Agree? So that kind of collisionless hash function, hash tables are not good. Okay, very bad. The actual computation is done by next number and is visited, right? To detect cycle. These three are the important things. Is visited, mark visited, and next number. They are taking practically no time. Okay. And once again, as I and AG mentioned, whether it is 99.15% or 98.23% or even 91 point something percent, it really doesn't matter, right? Anyway, this is a rough estimate, and it clearly gives you an indication that I have to do something about init.
Excuse me, sir.
Tell.
Like is visited function like an is set to 1. That is very simple only because of how we implemented the data structure, right?
True, it's a collisionless search function as table, right?
So if we change the data structure in init,
We will do.
then is visited is also like domino effect is there.
We will see. Let us make some 2-3 more attempts and see how we can improve this. But one thing is obvious. This profiling says that I have to do something about this init function. Okay.
Yes, sir. Okay.
This much is obvious, right? Okay.
Yes.
So let us make a second attempt. Okay. So you need to look at the, I would say, structure of the problem at hand. First of all, you note that if n is greater than or equal to 100, the next number n is less than n. Okay, you can easily prove this. But if n is less than 100, next number may be bigger than n. For example, if it is 99, the next number will be 162. Even though this is bigger than 99, it is not bigger than 200. This is the maximum possible thing. Okay. And if I restrict to all 32-bit integers, then the maximum possible value of next number n is 3 followed by 9999 9 times. So this is 738. Okay. So what if I do something like this? Okay. If n is less than 100, we take a to be of size 200. And if n is greater than or equal to 100, we take a to be of size 1000. Of course, instead of 200, I can choose something like 163, 164. Okay, but this is fine. And here also I could have taken 739, 740, something like that, but I have just taken 1000. Okay. And what I will do before calling ishappy n, I will first make one iteration of next number and I feed that thing to n. Okay, first replace by this so that it is significantly reduced and then just call ishappy n. Okay, so this is a fairly straightforward, I would say, attempt to improve upon the previous code. Agree or not? So if n is something like 10 power 5, so I was using an array of size 10 power 5 plus 1. Now I am using an array of size at most 1000. So it will definitely take much smaller time. Okay. And then if I do this, I would say, profiling. First of all, I see that what was the earlier time? Something like 100 microsecond, right? You remember? Total time is 193 microsecond. Okay. And with this new implementation, ishappy is now taking less than 2 microseconds per call. Okay. So it's something like some 50-60 fold improvement. Okay. However, if I look at these percentage contributions, I see that init, although it has been, I would say, very significantly improved, this is still taking something like 90% of the time. So instead of 99%, it is now taking 90% of the time. Okay. Next number and ishappy are now in the picture somewhat, but visited and they are also in the picture. Instead of 0.00%, there's something. But although this init is better than the previous init, there are still scopes for improving this init function. Agree? So again, I say whether it is 90.17% or 80.25%, this does not matter. I can still see that init is the culprit. Only this much information I would say, interested in, and gprof is good enough to supply this kind of information. Again, if you add these things up, it will not be 100. Maybe bit greater than 100, less than 100. That doesn't matter. I can still see that init is the culprit. Agree? Okay.
Yes, sir.
Okay. So that much is where I am getting the help of gprof. Okay. So this is not a very exact timing, but still I see that this is the culprit. Okay. So I have to generate other ideas to make this function more efficient. Okay. So now from 93 or 90 something like microsecond, I have 1.5 microsecond. Okay, I want to make it even better. Okay, so this is the third attempt. So I will make another improvement of A. Instead of designing it as a hash table. Okay, so we'll use a simple array to store the numbers already generated. Okay. So now A is an array of size 1000, but I will not initialize every cell of A. Okay. Okay. Instead, I will use A as an array. Whenever a new number is generated, I will simply append that array with that new number. Okay. So let's see. Mark visited appends to A each new number generated in the sequence. Okay. Of course, for that matter, you also need to store externally how many integers are saved in A. Okay. And then A is not necessarily sorted. Okay, so I will not make an attempt to sort A. Okay, so A's visited makes a linear search in A. Binary search is not possible. Okay. And for a sequence of few tens of numbers, of course, I could have a better, I would say, implementation of A, like a height balanced binary search tree or a sorted array, something like that. But eventually what happened in the, I mean, you will generate a few tens of numbers. Okay, 20, 30. So designing a more sophisticated data structure for this dictionary may fail to produce better results, but of course you can go ahead and try what is happening. Okay. But I would say implementing a binary search tree, height balanced binary search tree, that may be an overkill. Okay. For such a few, such a small number of numbers. Okay. Now, if I make a profiling analysis, once again, don't worry about these exact things. You see that init is now no longer taking enough time in percentage contribution. Because even I am just setting the total number of, I would say, entries initialized, that to 0. Okay, so that's not much in it. Okay, therefore, the percentage contribution of init has significantly reduced. But now I see that is visited has become the primary culprit. It's now taking about 50% of the total time. Next number is taking something like 1/4 of the time, and the remaining things add up to the remaining 1/4. Okay. And that is expected because as visited is making linear search. Okay. As you insert more and more elements in the array A, the search becomes more and more costly. Agree? So now I focus my attention on is visited. So one possibility that I mentioned here is that go ahead with some more sophisticated data structure like a height balance tree or even a sorted array so that you can make binary search instead of linear search. What things will happen? That requires an experimentation, but what I want to show you, what was the absolute time in the second attempt? 1.69 microsecond. Okay. And with this third attempt, EaseHappy is now taking 247 nanosecond. So how much improvement is that? 1. What was that? 1.69, 1690 nanosecond. Instead of 1690, it is 247 nanosecond. There's something like 6-7 fold improvement. Is it not?
8 times. 8 times improved.
Something like that. Not 8, 7. 6 point something. Okay. But still it's, yeah, 7 times 24 is 168. Yeah. Anyway, whatever it is, it's already a very significant improvement. Okay. So the question is, can I make it even faster? Okay. So here is our last idea. And this actually calls for a deep mathematical insight into the code or into the problem, I would say, just by making these data structures more efficient will not lead to this fourth attempt. Okay. So let's say algorithmic improvement suggested by your discrete maths professor. The idea is something like this. Every happy number essentially reduces to 1 by definition. And every unhappy number ends up in a cycle. What is very important here is that every unhappy number ends up in the cycle containing 4. Do you remember the 2022 cycle? It contained 4. So whatever the unhappy number is, it will eventually end up in this cycle. No other cycle. Therefore, you do not need to remember anything which numbers are generated or not. If you eventually come to 1, declare that number as happy. If you eventually come to 4, declare that number as unhappy. Why is this true? Don't ask. Okay, this is a discrete math assignment. In fact, I have told everything earlier in order to arrive at a proof by induction. Okay. So there is no need to maintain any data structure like A to store the numbers generated in the sequence. If 1 is reached, declare it as happy. 4 is reached, declare it is unhappy. Okay. So only thing is that in a loop, you keep on generating next numbers, check whether it is 1 or 4. If 1, immediately return 1. If 4, immediately return 0. Okay. So now if I make a profiling analysis, I see that the next number, which should do the, I would say, most amount of computation, this is taking 82.27%, is happy. The second one, this main is taking a little bit of time. More importantly, what was the previous thing? 247 nanosecond. Okay, about 250 nanosecond per call. Now it has become something like 60 nanoseconds per call. Okay. So we started with something in the level of microseconds, right? And now we are just 60 nanoseconds per call. Okay. So now you may think about how you can improve upon next number and so on. And this process will never end. Okay. But anyway, every time we have got something like 5 to 10 fold benefit. Okay. And this was possible because there is a profiler which, although work approximately, gives us the indication which function I should look at. Eventually, I may have to use something like an algorithmic improvement. Okay. So that's how it works. That's how you can exploit the help provided by a profiler like gprof. Agree? So I will stop my attempts here. There may be a fifth attempt that will make it even more efficient, but this is already good enough, right? As a demonstration. Yes or no?
Yes.
Okay. Okay, so what remains is an explanation of the call profile. So what was the file flat profile? Now we will see the call profile and a couple of uses of this call profile. A record for each function delimited by a line consisting of dashes. Okay, the profile you have not yet seen. Okay, I think we should see an example, a line starting. I'm just reading this line starting with this is a primary line for a function. Above the primary lines, all the caller functions are listed. Okay, and below the primary, all the called functions, and for each of these calls, it's the percentage time, and so on. Primary line has a single call count. If it is a non-recursive function, if it makes recursive calls, two numbers, count 1 plus count 2. Count 1 is the number of non-recursive calls, count 2 is the number of recursive calls. Okay, and for a caller or called function, there are two call counts, count 1 by count 2. Let us look at an example instead of just reading these things. Most of these things will be, I would say, written in a verbose fashion if you do not run gprof with the option -b. Okay, these things are already, every time you run gprof, you will see this kind of instruction, perhaps more detailed than this. Okay, now let's see what these things really mean. So understanding the call counts. Okay, so let's start with a very synthetic example. So I have three functions, f, g, and h. H calls f and g calls f. F does something. In this synthetic example, it does not do anything. Maybe it prints something, does some calculation, just for illustrating. And you call f for I equal to 0 to 100, g 0 to 200, h 0 to 300. Okay. And there is no recursion involved here. F calls g and f and sorry, h calls f and g calls f calls nobody. Agree? So now if I look at this graph, why is this called a call graph? Okay. Main is a function. This calls f 100 times. It calls g 200 times, h 300 times. Okay. Now if I look at h, it calls g, okay, f 300 times and g 300 times. Okay, so one call per invocation of h, 300 plus 300. But then if you see g, so it is invoked by main 200 times and by h 300 times. The total number of times g is invoked is 200 plus 300, 500. So g calls f 500 times. Okay. So how many times is f called? 100 plus 500 plus 300. That is 900. So this is what is meant by the call graph in pictorial form. Okay. What the call profile of gprof will give you, it's something like this. So this is called the primary line. Okay. So one function. Okay, one second. This is, I would say, listed in some sorted order anyway. So this dashed line above this corresponds to the records of f. Okay, So this thing essentially says I am talking about the function f. Okay. Above this f, we list. Okay, so this says that f is called a total of 900 times. And above this, who called f? It says that out of 900 calls, these 900 calls, 100 are made by men, 300 by H, and 500 by G. That's precisely what you see, right? F is called 100 times by men, 500 times by G, and 300 times by H. Happy?
Yes, sir.
Yes, sir.
Okay, so now let us look at the second function 2, which is G. If you look at G, it is called how many times? 500 times. So G is invoked 500 times. Out of this, 200 times by men, this one, 300 times by H. And it itself calls F 500 times out of 900 calls of F, right? 500 calls of F out of 900 calls of F. Likewise, if you look at H, just quickly browse through it. It is called 300 times by men. That is the total number of invocations of H, and all 300 of these invocations are by men. And it calls G 300 times. It calls G 300 times out of 500 calls of G. And it calls F 300 times out of 900 calls of F. Men
Sir,
is
this
not.
thing we have already seen above also, like it is calling F 300 times out of 900.
Yeah. Many things are repeated here, but anyway, it's a complete information about the function H. Okay, who called? How many times I'm called? And how many functions I am calling. Okay, so several entries are repeated, but anyway, that doesn't matter. Okay. Okay, and main is not called by anybody, so that's why it is said it is spontaneously called. Okay. But it calls H 300 times, G 200 times, F 100 times. Okay. Out of 300 calls of H, 500 calls of G, and 900 calls of F. Okay.
Excuse me, sir.
Yeah, tell.
Sir, is there any significance of the index number, like F is having 1, G is having 2?
I think it is once again in some sorted order, but in this case, it's running for so small amount of time. So it misses almost all the samples. So this total is 0. So let us look at this. Next one. So this is happy numbers third attempt. Once again, you see that this is, I think, percent time this time. It's something like percent time in the function plus the called functions. So man is taking 100% time. Then is happy is taking 96.1% time, including function calls. Is visited 51%, next number. So it's sorted in this order and it gives this number 1, 2, 3, 4, 5, 6 in this decreasing order. Okay. And you see that in the earlier case, this program ran so fast that it misses all the samples, and therefore this 0, 0, 0, 0, 0, it makes no sense. If it runs for some time, you get some meaningful percentage times, and it's something like this. And this indexing is with respect to the decreasing order of this time. Fine. And who is calling whom, how many times, and so on. Okay.
So what is meant by children? Like what does the number represent?
What?
What does the column children represent?
I think it is self-time, and children means called function time. Okay. Inside the main, it was for 0.01 second, and in function calls, it took something like 0.25 seconds. Total is 0.26, which accounts for 100% of the total running time. Something like that, possibly. Okay. But counts, you see, these are the counts. Okay. But anyway, if you want to look at the timing estimates, I would suggest that you look at this flat profile, timing profile. That gives you more detailed information. This is mostly relevant for looking at these call counts. Agree?
Yes, sir.
Okay. So now let us see how this call counts can also give me an indication of improving a function. Okay. So for that matter, I will write what is called a recursive call graph Fibonacci functions, Fibonacci. So this is the standard thing taught to you in PDS. Okay. N less than 0, return -1. Okay. And let's say we give only positive values for n or non-negative values. If it is 0, return 0. If it is 1, return 1. Otherwise, return recursively compute fib n -1, recursively compute fib n -2, and add them, return that value. Okay. So let's say we call fib32 from main. Okay. And if I now make a call graph profiling of this program, I see that this function fib is called only once non-recursively, that is from main, and it itself calls, okay, it calls itself these many times, 7049154 times. Okay, here also it's called one out of this one non-recursive call itself, and fib is called this many times. Recursive, fib is called by fib this, fib is called by fib this, so these three numbers should match. Okay. So you see, the call of fib is made recursive calls too many times. And of course, you know why this thing happens, right? Fib32 calls fib31 and fib30. Fib31 will also call fib30. So the function is the same, I would say, argument or parameter is called many times. So that is the problem with this. Okay, so how can I improve upon this? You should know about your algorithms. Yes.
This linear time algorithm we can write remembering previous two values.
Yeah, so that is one possibility, replacing recursion completely by iteration. And if I continue to
memoizing,
yes, continue to exploit this, I would say, recursive structure, another possibility is doing memoization. Okay.
Sir, or we could use that discrete math formula and
Yeah,
we
yeah,
can reduce it to log n.
Yeah, that's true. So I will illustrate what we will do, the memoization. Okay. So I hope you know this idea. In main, we initialize this element of an array to -1. Okay. So n is 32, so this is not a huge effort. And we pass f along with n to this function. And in nf, we first check whether fn is greater than or equal to 0. Essentially, this means that it is computed, return this value. Otherwise, okay, we set fn. If it is 0 or 1, just set f0 to 0 or f1 to 1. Otherwise, make a recursive call and return fn. Okay, this is a standard memoization idea. And in the main function, you call this. Okay. And now if you see the call graph profile, you see that recursive calls are definitely made, but starting what was the earlier thing, 7 million. Instead of 7 million recursive calls, I have now made only 62 recursive calls. In fact, you can write these two codes and make timing profile. You will see that the earlier implementation was very, very slow. This is now quite good. You do not actually require the profiler to understand this. You just run it, you will yourself figure out. Okay, so this is the end of the slides for today. Yeah, tell.
Sir, I have a difficulty understanding the call graph for recursive function because the number of entries in the name column are reducing as we go from 1 to 7. How is that happening exactly?
Fib. Okay, so this one is the primary line. It says that I am talking about the function fib. Okay. The total number of invocations of fib is 1 plus 62, that is 63. Out of this, whatever appears here is a non-recursive call. And after plus whatever count is appearing, this is the number of recursive calls. How many times fib calls fib? Why is this 1? Because in the outermost level, main called this fib, right? So
yes, sir.
1 out of 1 non-recursive calls is made by main. And 63 out of actually 63 calls is a recursive calls made by fib. Fib calls fib 62 times, and this also says basically the same thing. Fib calls fib 62 times. Is it clear now?
Yes, sir. Yes, sir.
Okay. Yeah, so that's it. Okay, so I think I should stop here. If you have any immediate question, let me know.
After that, can I have 5 minutes?
Yeah.
So let them ask the questions first if they have any questions.
Yeah, tell. What do cycles mean in the recursive calls? Cycle. Where is cycle?
Sir, I can see that the means when I get the information about gprof, it's talking about cycles and numbering of those cycles.
Cycle is not listed here, right? I don't understand where you're talking about cycle.
Sir, it's saying that if there are any cycles in the call graph, there is an entry for the cycle as a whole, etc. So like.
Oh, I see. Cycle means here, of course, fib is calling itself, but it is possible that fib is calling, f is calling g, g is calling h, and h is calling f. So that's not a direct recursive invocation, but it's a cycle of recursive invocation. Yeah, so what thing will happen there, we have to check. Yeah.
What gprof does, I think, is, as you just read it out basically, the student, it will show basically still a recursive call of fib. So for that cycle, it will show as a one entry for fib's recursive call basically.
Okay. Anything else?
Any other questions?
No. Okay, then I stop my screen sharing.
Yeah, so I just a couple of things. One thing that you should keep in mind that, so this was a program that did not take any parameters. Okay. So when you take a parameter, the time that your program takes will depend on the parameters. It may take very little time, it's a very long time. So when you use profiling for programs that will usually have a lot of parameters, okay, for general profiling thing, you should actually try it with different parameters. This is similar to what you will learn in software engineering for testing actually. Okay. Or sometimes you profile because you see that one specific set of parameters, the program is running very slow, then you obviously test with only that parameter set. So that's just something to keep in mind. Okay. So you just you don't profile with only one set of parameters for program that takes parameters. Okay, the other side is I figured out what gprof is doing. So we'll resolve those questions today itself, if you allow me a few minutes. So basically, I don't have a tab with me today to draw, but I think you will understand. So when you compile with -pg, okay, what GCC does is actually put something in the source code, not actually write it in the source code file, okay, but put some calls in the source code file before it compiles this. Okay, and I will kind of put it as a layman's view right now because you don't know any architectural ways to understand this fully. So it basically puts some things plus this main call called profile. This is a Linux specific call. It's a Unix like system specific call. So profile, the function, okay, which gives you some information about who is running currently. So think of that at the beginning of some sample period, it calls the profile to figure out who is running and in which function and so on. Okay, so it injects that thing at the beginning of every function and so on. Okay, so and then it collects that information. That is the one plus some other things it writes in that gmon.out file, which gprof will do the statistical approximation later on to find it. Okay. So the times that you get are actually the function times, which is not the profiling time actually. Okay, it's only if the OS tells you that it is this particular program is in this particular function, you collect that information. So it is the profiler function, then it won't be that function basically. But again, I was trying to visualize the code. I did not see that gprof code actually. I saw it design. Okay. So I think it will get affected a little bit with the time. But again, since you're not looking at the accurate time, it doesn't really matter. Okay. And your IO times and all will not count this scanf question, because then when the sample you take, because the program is not running, as we have noted that the program does not actually use the CPU at that time. Okay. So the sample will not report that this program is in that function, the function that contains the scanf at that time. So so IO time will be completely different. So that will not factor in here at all. So IO time will not be counted. What you get is mostly the program time. I cannot guarantee 100%, but the 10 millisecond time actually comes from that profile call. So the profile call has an inbuilt 10 millisecond time out there. And I was just looking at other profilers and all, everybody profiles for around in the millisecond order only, okay? Simply because otherwise, when you profile, your program is going to take too long. And again, kindly remember that these are very small programs that you're profiling when you're looking at the examples. Typically, you try to improve performance of programs that anyway runs for a long time. And then because you compiled with -pg, if your profiling information makes it run 3 times slower or something, then it becomes an inconvenience basically. So this 10 millisecond is not a gprof specific thing. Okay, gprof basically just calls a Linux profiler, which has the 10 millisecond built in. It's not changeable out there. Okay, and you get, as I said, the IO times are not counted, and what you get is basically mostly almost all, I would not use the word 99% or something, the actual function time. Okay, but then there's yes, it's not the actual running time, there's a statistical approximation of that. So that mechanism I will not go into details out there, but it's kind of, you take these samples at 10 millisecond time, it says in this sample the program is in this function, in this sample is in this function, in this sample is in this function, so on. And over a period of time you compute a histogram saying how many samples I found out of this 10 millisecond time which said that it was in this function f1. And how many samples said it's in function f2, how many samples said in function f3, and so on. Okay. And based on that and some other things, you make a statistical approximation of the times of that thing, functions basically. That's what you see out there. So that's the overall thing. If you want more details, send me a mail. I don't think you will understand fully right now, so I don't think you should go for more details, but I'll send you the original design paper of gprof, which has a very nice description. But then some architecture OS aspects that you will need that you may or may not know right now, basically. So I think we'll keep it at that. If you have more questions, you can ask us offline.
Sir, you said something like the running time depends on the set of parameters. What was
Right.
that?
Oh, that's a different thing from the last part. See what I'm saying. See, suppose you have a call. Think of your main program. Okay. In your main program, you say some parameter A that you passed from the command line is so that if A less than 100, you call one function, else you call another function. Okay. Now, let's say if A less than 100, you call F1, else you call F2. Now, if you keep on giving parameters that are greater than equal to 100, F1 will never be called. And F2 may be very fast function, implemented very well. So you think that your program is running very well, but then it goes to the customer and the customer gives 50 as the parameter. It calls F1, which never got run in your testing basically. And F1 may be a very badly implemented function for some reason, which is where you wanted to improve the performance, but you never got an idea from your profiling that the F1 function is actually taking a lot of time. So, for example, in this simple case, you should test with both parameters that are less than 100 and parameters that are greater than equal to 100.
Okay, sir.
Okay. Same thing you will see in software engineering when you do testing. Your testing should actually, there are words like code coverage and everything kind of. You should put parameters, you should put test cases, they say basically, such that every part of your code is executed. Otherwise, there is one part of code, if it's not covered by the test case, if there is a bug in there, you will never be able to detect that. It's a very common sense thing. The same thing for performance profiling also.
Yes, sir.
For example, if you want to run quicksort,
exactly.
You get different types of samples, nearly sorted, random, okay, that kind of stuff. Yeah.
Okay, sir.
Any other questions? So one thing again, I think it is clear, but still, since we are on the topic, so the command gprof is just processing a file. The gmon.out file is doing all the statistical approximation, all these things. The actual samples collected are collected because you introduce some code. Because of that, the GCC actually introduced more code in your source code before it compiled it, because it saw the -pg option. So when your code ran, those samples were collected and actually written into the gmon.out file.
So there was one more. So there was one more gprof related flag given inside, which was a newer version of that. So shall we use that or gprof?
What is that? I didn't get your question. Can you please repeat?
Sir, there was an alternative to gprof given in the slide.
Alternative to gprof, AD? What was the alternative?
gcov.
gcov. Okay, gcov
yes,
is
sir,
different.
gcov.
Okay. gcov is line-by-line coverage.
Oh, okay, my bad.
Okay. gprof is function level coverage. Both are important. So it's not a question of use this or that basically. At the beginning, you probably want basically, function level coverages basically. And just a rule of thumb, basically we look for both functions that take a large, when you do a gprof profiling, we look at both functions that take a larger amount of time compared to other functions per call, okay, and also functions that are called a large number of times. The reason being, you need to be wary about those functions because they're called a large number of times. Right now, maybe they are not taking too much time per call. But if you change something, okay, you should be careful knowing that this function is actually called like a million times. So even if there's a small increase in its time, the total time increase in the entire program will be very large. So this lab, as we have told in the first class, it kind of starts you off thinking. Okay, it's up to you how to go basically, because most of these things are useful for when you have large programs. Okay, you work in groups, large, as we have said in the first class. So you should kind of, even though you're writing smaller programs now, you should kind of get into this mindset. And every program that you do, just do a profiling to see, what is happening and so on. So the absolute values will be very small. Program will run very fast. But still, it would be nice to see proportionately if some function is taking too long time and just to investigate, can I make it better or something, just for practice sake. Okay, I'm done. Is there any other questions?
Sir, these time calculations are done when we execute a.out, right? No pre-computation such is.
No. It's not even done during when we execute it. A.out. So think of it this way. Okay, I'll give you just one part of the very simple thing. At beginning of at every 10 millisecond time, okay, you inserted a code, okay, that just collects a sample, collects some information. Okay, so a.out does not do any calculation. A.out just collects these values, okay, which are actually written into memories, not to slow down the program. And when the program executes, the a.out exits, okay, it writes it in the gmon.out file. The actual calculations based on those values collected is done by gprof when it reads the gmon.out. The input to that calculation is collected when you run the a.out execute.
Okay, understood, sir.
Any other questions? Okay, so if not, I think Eddie, we can close, right? Yes, Eddie may have gone off for a second.